Module 10, Cohort Studies. A cohort study is a type of analytic observational epidemiologic study. Cohort studies may also be called concurrent, follow-up, incidence, longitudinal, and prospective studies. Key components of the cohort study design is that the source population is defined by exposure status. Subjects are observed over time, commonly years, and the incidence rate of the outcome is calculated and compared between the exposed and unexposed. The origin of the term cohort comes from one of the 10 divisions of a legion in the ancient Roman army, a military unit containing 300 to 600 men. So visualizing this defined group of soldiers moving forward into battle may be a useful way of remembering the key feature of an epidemiologic cohort study where people are observed moving forward in time. In a cohort study, the investigator defines the source population of interest and selects a group of exposed and unexposed individuals from amongst those at risk of the outcome. These individuals are followed over time and the incidence of the outcome, death, disease or other, in the two groups is compared. If a positive association exists between exposure and outcome, we would expect the incidence to be higher in the exposed compared to the unexposed. A cohort study can be prospective or retrospective. In a prospective study, the investigator selects the study population at the beginning of the study and follows the subjects concurrently over calendar time until the outcome develops or does not develop. A retrospective cohort uses historical data to identify a pre-existing study population and their exposure status, and the incidence of outcome is then calculated at the current time. A cohort study can also have combined prospective and retrospective elements, whereby exposure is ascertained from objective historical records and subjects followed up over calendar time until outcome develops or does not develop. A double cohort study is distinct from conventional single group cohort studies in that two distinct populations are involved with different levels of an exposure of interest. Double cohorts are employed when the exposure is rare and a relatively small number of people are affected. For example, persons exposed to radiation after Chernobyl or workers at a viscose rayon plant exposed to carbon disulfide. A comparison group is then selected that is similar as possible to the exposed group but with no exposure. These may be a sample from the general population or from a similar group, such as workers from a different factory in the viscose rayon plant example. A cohort study should be conducted when there is strong evidence of association between the exposure and outcome of interest, that is, from cross-sectional or case-controlled studies. There's a relatively short time interval between exposure and outcome development. Like I mentioned previously, this may still be years, but it might not be practical to follow a cohort over 50 years or more. And finally, due to the cost and time required to conduct a cohort study, the feasibility is enhanced if several study questions can be answered through a single study. When defining the source population at the beginning of the study, it's necessary that the exposure is not rare, so that there is a large number of exposed individuals, that there's an appropriate and feasible method available to measure exposure accurately, that there's an unexposed group available. For instance, if everyone in the cohort was exposed or were exposed to the same degree, you wouldn't be able to evaluate the influence of the exposure on outcome. And finally, the participants need to be at risk for developing the outcome, and therefore individuals with the outcome at baseline or who cannot develop the outcome, for example women in the study of prostate cancer, are excluded. To ensure that the source population has these required characteristics, a priori the study investigators develop an eligibility criteria which outlines the characteristics of the individuals to be included and excluded from the study. Based on these criteria, participants are recruited using either a community-based sampling frame so that the participants are representative of the general population, and as such the results of the study can be generalized to the population. However, it may be more feasible to identify individuals based on a single factor, such as their exposure, for example, studying respiratory diseases among coal miners, their outcome, for example, studying breast cancer in women with a family history of breast cancer, special groups such as nurses, physicians, civil servants, or by geographic location facilities such as hospitals, schools, or residential homes. The Framingham Heart Study is a long-term, ongoing study on residents of the town of Framingham, Massachusetts. The objective of this study was to identify the common factors or characteristics that contribute to cardiovascular disease by following its development over a long period of time in a large group of participants who had not yet developed overt symptoms of cardiovascular disease or suffered a heart attack or stroke. The study began in 1948 with 5,209 Framingham residents aged 30 to 62 years recruited and completed physical examinations and lifestyle interviews every 2 years with daily surveillance of the local hospital. The study is now on its third generation of participants, the grandchildren of the original cohort, which is pretty amazing. Prior to Framingham, almost nothing was known about the epidemiology of cardiovascular disease. Much of the now common knowledge concerning heart disease, such as the effects of diet, exercise, and common medications such as aspirin, is based on this landmark cohort study. Over the 65 years of research, the data obtained through the Framingham Heart Study has resulted in 2,500 published scientific articles. I'd encourage you to go to the study website to learn more about this cohort study and its contribution to our understanding of not only cardiovascular disease, but also other diseases such as osteoporosis and dementia. I will use one of these published articles to illustrate the concepts of the cohort study design. This paper, entitled Physical Activity and Stroke Risk, was published in the American Journal of Epidemiology 10 years ago. The authors state that they examined the influence of different levels of physical activity on stroke risk in both males and female members of the Framingham study cohort. This relationship was then examined at 2 distinct points in time, one during midlife and another when cohort members were elderly. In addition to examining the effect of low levels of physical activity on stroke risk, they compared the effect of high levels of physical activity with that of moderate levels to determine whether there was any additional benefit. As mentioned, the source population for this study were the residents of Framingham in the original 1948 cohort, and the study sample consisted of 5,209 individuals, 2,336 men and 2,873 women. The methods employed and source of information to ascertain exposure depends on the type of cohort, whether it's retrospective or prospective, the source population, whether it's a population-based or a specific group, and also the characteristics of the exposure of interest, where the investigators just need to identify if individuals were exposed or not, or if they require more detailed information such as timing, duration, and intensity. Commonly used methods include questionnaires, existing records, laboratory tests, physical measurements, or clinical examinations. These measures are often repeated as was the case in our example where subjects were evaluated every 2 years. In our example, the exposure data came from a questionnaire on daily activity levels, which was administered during examination 4 in 1954-5 and examination 11 or 12 in 1971-72 or 72-73. This information was then used to calculate a physical activity index for each subject, which was a composite score calculated by summing the products of the reported hours spent at each level of activity, that is, asleep, light, moderate or heavy activity, and a weighting factor based on the oxygen consumption required for that specific activity. These physical activity index values were then divided into exposure categories by dividing the cohort into tertiles of low, medium, and high physical activity levels. This is a common strategy when there isn't an unexposed group per se, and the low group is used as the referent. When measuring the outcome, it's imperative that the same method is used for exposed and unexposed subjects. and that it's clearly defined. In our example, the outcome was defined as the first occurrence of atherothrombotic brain infarction, cerebral embolism, or other type of stroke. Data on outcome can be obtained through death certificates and other records of mortality, hospital and physician records, employment records, reporting of the subjects, such as from a questionnaire or a diary, lab tests, physical examinations, or other clinical procedures, such as X-rays. In Framingham, data was ascertained during the biannual follow-ups and from daily surveillance of the local hospital where subjects suffering a stroke would present. When the cohort study ends after a defined period of time, the data can be analysed. Commonly used effect measures in cohort studies are incidence, relative risk, and attributable risk. Table 7.5 in Chapter 7 of the Merrill text defines these measures. The confidence interval and/or p-value associated with the effect measures provides information on the statistical significance of the association. For these statistical measures to be meaningful, it's imperative that the sample size is big enough to be able to detect an association of a certain size if it truly exists. We call this adequate power. This graph is taken from our example article. It shows the age-adjusted cumulative incidence of stroke in women during the 18 years of follow-up from midlife to old age in the Framingham study by physical activity tertile. You can see that the incidence rate of stroke appears to be highest in the low physical activity group and lowest in the medium activity level group, but this difference changes in the latter part of the study, probably the last 4 years of the study. The 2x2 contingency table for calculating effect measures will be familiar to you by now. The risk ratio, which you were introduced to in Module 6 on causality, is the measure of association used in cohort studies and is calculated as the cumulative incidence rate in the exposed divided by the cumulative incidence rate in the unexposed. If the total time at risk each subject is available rather than the total number of subjects in each exposure outcome category, then the rate ratio is calculated by dividing the person-time incidence rate in the exposed by the person-time incidence rate in the unexposed. This table shows the crude and adjusted risk ratios of the association between physical activity level and stroke in male participants of the cohort study. We observe that a moderate or high activity level is associated with a lower risk of stroke, and this association remains after adjustment for age and for other risk factors. In the multivariate analysis, it appears that the protective effect is stronger, risk ratio of 0.41, with moderate activity level than high activity level, which has a risk ratio of 0.53, indicating a 59% and 47% reduction in risk of stroke, respectively. These conclusions are supported by highly significant p-values and tight, that is, precise confidence intervals that do not straddle 1. Another effect measure that we have not yet covered in this course is called the attributable risk. If the association is assessed to be causal, this measure tells us the amount of disease in the exposed that is due to the exposure. It's a function of both the exposure prevalence and the strength of the association. The individual attributable risk is the difference in the incidence, either cumulative or person time, between the exposed and unexposed. The population attributable risk is the difference between the total incidence and the incidence in the unexposed. Unfortunately, the authors do not report the exact number of cases in each tertile, but this can be estimated by working backwards from the risk ratios and the total number of subjects and cases. So we're able to estimate the attributable risk. To make this measure more meaningful, I've assigned the low exposure group as unexposed and the moderate high physical activity groups as exposed. So we see that 11 cases of stroke per 100 inactive males are due to their inactivity, and that 2 cases of stroke per 100 males in the population is due to inactivity. The attributable risk percent is the proportion of cases of disease among exposed individuals that is due to the exposure. So in our example, we can say that 66% of stroke cases among inactive males is due to being inactive. The population attributable risk percent tells us the proportion of cases of disease in the entire population that is due to exposure. And in our example, we estimate that 25% of stroke cases in the male population are due to inactivity. This means that if the entire male population became at least moderately active in their midlife, we would expect to observe a 25% decrease in the incidence of stroke in older age. Like cross-sectional and case-control studies, the validity of the findings of a cohort study can be threatened by bias. Potential selection bias, which you recall is when subjects included in the study are systematically different from those not included, are due to loss to follow-up or a healthy worker effect. Loss to follow-up is a common problem in cohort studies, increasingly so in cohorts with longer follow-up times, and occurs when researchers lose contact with study participants, resulting in unavailable outcome data on these people. Reasons for this attrition include refusal to participate, that they're unable to locate them, unable to be interviewed, or because of death. If the final study sample is systematically different from the source population with regard to the risk of the outcome, then a bias may result, leading to a spurious association. As a rule of thumb, losses should be no more than 20% to rule out selection bias. A healthy worker effect bias can arise when outcomes among workers are compared to a general population sample. The bias is due to the fact that workers tend to be healthier than the general population because you need to be healthy to work, and as a result have a lower risk of disease or mortality. Observation bias is also a concern in cohort studies. This can occur if the quality of information collected differs by exposure status. This is sometimes referred to as diagnostic suspicion bias, whereby knowledge of exposure leads investigators to look more closely for the outcome in exposed subjects. Misclassification is again a concern in cohort studies. Differential misclassification arises if classification of the outcome is somehow related to the exposure status, leading to a distortion in the risk ratio. This distortion can be in either direction, that is, an under or overestimation. Non-differential misclassification may arise by inaccuracies in classifying exposure status of individuals, but these misclassifications occur similarly between exposed and unexposed groups and result in a weakening of the observed association, that is, biasing the risk ratio towards 1. Investigators must try to eliminate or control for the influence of confounding. This might be done through restriction or at the analysis phase through a stratified or multivariate regression analysis. In our example, the investigators used some restriction by only including adults over the age of 30 and up to 62, and they adjusted for age, BMI, blood pressure, cholesterol, number of cigarettes smoked per day, total vital capacity, glucose intolerance, atrial fibrillation, valvular disease, congestive heart failure, occupation in the multivariate regression analysis. In addition to controlling for confounding, it's important to evaluate if effect modification is present. You recall that this is when an association between an exposure and disease outcome is modified by the level of an extrinsic factor beyond random variation. In our example, the observed association between physical activity level and stroke differed by sex, with moderate and high activity having a statistically significant protective effect in males, which we saw a risk ratio of 0.41, but no such effect was apparent in women, with a risk ratio close to 1. The presence of confounding and effect modification can be evaluated through a stratified analysis. If the risk ratio is the same or similar across the different levels of a potential confounding variable in the stratified analysis, but is different in magnitude from the crude risk ratio, then confounding is present. If the crude relative risk or risk ratio is greater than the stratified, it is termed positive confounding. If it's smaller, it's termed negative confounding. If the stratified odds ratio or risk ratio are different across the strata, the effect modification is present. Confounding needs to be controlled while effect modification is described, as in our example where the results were presented separately for males and females. Once the internal validity of a study has been established, a final step in interpreting the results of an epidemiologic study is to consider its external validity, that is, the degree to which the results of a study are relevant for populations other than the source population. This is known as generalizability. One of the criticisms of the original Framingham cohort used in our example has been that it was not a very ethnically diverse group of individuals. Therefore, the results may not be generalizable to non-Caucasians. In addition to the Framingham cohort study, there has been several other landmark cohort studies that have provided invaluable epidemiologic data on a variety of exposure outcome associations. I highly recommend that you take the time to learn more about some of these. In summary, cohort studies compare incidence of disease, that is, an outcome, between exposed and unexposed groups. They're conducted over time, and they allow for inferences to be made regarding possible causal associations. The ability to be able to establish temporality is one of its main advantages, as is its use to study rare exposures, measure and study multiple outcomes, and minimize recall bias. However, cohort studies do tend to be expensive and labor-intensive and may be inefficient to study rare diseases or those with a long latency period. In Module 9 and 10, we have reviewed 3 types of observational analytic study designs, namely cross-sectional, case control, and cohorts. In the second lecture in Module 10, we will discuss another type of analytic study, the experimental study.